We're going to continue working with the same card game that we talked about in the last video. So it costs me $1 to play. We draw one card from a standard 52 card deck, and we can win various amounts of money depending on what it is that we draw. In this video, though, we want to talk about two things. We would like to talk about the expected value of the game and then whether the game is fair or not. So looking at part A, it just says find the expected value of the game. Now, I've gone ahead and just brought down the probability distribution that we worked out in the last video. I've kind of copied that down here. Finding expected value is much easier if you have the probability distribution in front of you. And you'll see as we start working through this, it's going to make our work in part A a whole heck of a lot easier. So if you look in the section above this, I gave a formula for expected value, and it might look kind of intimidating at first. But once you've seen it a couple times, it's relatively straightforward. It's just going to be multiplication and addition. So for every single outcome, I'm going to take the outcome, which in this case is the profit, and multiply it by the probability for which it occurs. So I'm going to take $19 times 0.019. I'm just using the decimal version of the probability that we found above. So I'm going to take $19 times 0.019. And I'm going to do that for every single outcome. So I'm going to take $9 times the probability for which it occurs, 0.077. So $9 times 0.077. And then I'm going to do the same thing for $1 times 0.231. It's probability. So $1 times 0.231. And then same thing for this last outcome right here. Doesn't really matter that it's negative. I'm still going to take that -1 and multiply it by its probability. So -1 times 0.673. And once I have all of those, I'm going to multiply those together and then just add the results. I'm just going to add all of these together. And you can do this all in one step if you want. So I'm just taking, again, the outcome times the probability of that outcome for every single possible case, outcome times probability, outcome times probability, and then I'm going to add the results together. So I'm going to grab my calculator here, 19 times 0.019 plus 9 times 0.077 plus 1 times 0.231 plus, in this case, -1 times 0.673. And I ended up with 0.612. And in this case, what this represents is this represents the average amount that you can expect to win if you were to play this game many times. Think about tens of millions of times, really infinitely many times, but millions, billions of times that works too. Now, you're never actually going to win this amount of money. What this represents is if you took the amount that you either won or lost every single time and average those together, this is the amount that you would end up with. You would end up with $61.2 cents right here. The notation that we use for expected value, there's a couple different ones here, just so that we can talk about that. You may see like E of X, that means the expected value of the random variable X, or you may simply just see the mean, mu. So all of those represent the expected value or the mean of this probability distribution. So in this case, you would expect on average to win 61 cents or 61.2 cents every time you play this game. So if it's me, it's in my best interest to play this game as many times as I possibly can, because I know in the long run I'm going to average roughly 61 cents. Sometimes I'll win and sometimes I'll lose, because I did have that instance of the -$1 profit, but on average I'm gonna win in the long run, which leads me to my next question right here. It says, hey, is this a fair game? And explain why or why not. And all I'm doing to determine if this is a fair game is I'm looking back at my expected value. In order for a game to be fair, I need the expected value of the game to be exactly 0. And what that means is it doesn't favor either player. It means you're going to break even. Sometimes you'll win, sometimes you'll lose, but in the long run, you should break even. If it's not 0, if it's not fair, then that means that the expected value is just not equal to 0. Now, it's easier to see in some situations than other. If you have a negative expected value, so if, for example, just to give an example here, if your expected value had ended up being, let's just say, I'm going to make up a number, negative 0.531, that would mean you lose roughly 53 cents on average every time you play this game, which that's a little bit easier to see. Whoa, no, I don't want to play that game because I'm going to be losing money in the long run. But what can be difficult to remember is it can be unfair and favor you as well. You don't think about that quite as much because, hey, it favors me. That's great. I'm going to keep playing this game. So in this case, we had a positive expected value, 0.612, which is not 0. All I'm just checking to see is that exactly 0, yes or no. So in this case, this is not fair because the expected value is not 0, and that's all I'm looking at to make that determination. And what's really cool is if you can create this probability distribution